Hi everyone, we are starting a new unit today, our last unit in fact, on trigonometry. And before we start getting into the new material on trigonometry, which is going to extend on what you learned last year, I want to just do a quick review on what you did in 10C with regard to trigonometry. Okay, so trigonometry is basically based on similar right triangles. The fact that all triangles that are similar to one another have equal proportions. The sides of similar right triangles will be proportional to one another. And those proportions have basically been stored in the memories of your calculators. Okay, so for example, if you have a particular triangle, a right triangle. In fact, I happen to know this one, so I'll just use this one, where this is 31 degrees, okay, and this has a height of 3 and a base of 5, okay, then any other right triangle with a base of 5 and a height of 3 with those proportions. So let's say we have another one, and this is 1.5, and this is 2.5. Okay, same proportions, because I've just cut them both in half. This will also be 31 degrees. Okay, and that's basically just similarity. And so what mathematicians did was they decided, you know what, these right triangles come up a lot in everyday life, and so we're just going to store these ratios in a book somewhere. And that used to be called a logbook, and people actually had to carry these around. Not so long ago, maybe 50 years ago, people had to carry around a logbook with all of these different ratios for a different angle down here. So if the angle was 30 degrees, the ratio would be slightly different. You'd have to go and look up what that ratio was. And of course, there's a third side, which is the hypotenuse. We can figure out what that side is using the Pythagorean theorem. So 3 squared is 9, 5 squared is 25. So 3 squared plus 5 squared is 34. So this would be the square root of 34, right? This side over here, which is about, let's see, square root of 34 is, I'm just getting a calculator. Let's see. The square, you can see I'm just kind of making this up on the spot here. Square root of 34, that's about 5.8. Okay, so on this one, by the way, it's going to be about half of 5.8, right? So if I divide that by 2, this one is about 2.9, because all of the sides in this smaller triangle are half of the bigger one, okay? And so all of these various sides were stored, the ratios, I should say, of the various sides were stored in something called a logbook. We don't need logbooks anymore because these ratios are stored in the memories of your calculator. And so in any triangle, we had to come up with a name for the various different sides of a triangle with respect to a specific angle so that we could record the ratios of their sides. And these are the names that we came up with. So if you have a particular angle, let's say we're talking about this one, okay, then firstly the hypotenuse is always called the hypotenuse. And these only apply to right triangles, by the way. The side that's across from the angle, which is this one over here, is called the opposite side. And the side that's beside the angle that's not the hypotenuse is called the adjacent side, okay? Now, if you want to take ratios where you pair sides up and you've got 3 different sides, there's 3 ways to pair up the 3 sides. And so there's 3 trig ratios. So in no particular order, one of the trig ratios is called the sine ratio. And the sine of an angle is the ratio of the opposite side to the hypotenuse. Okay. We can also, so we've now paired up opposite and hypotenuse. We can also pair up adjacent and hypotenuse, and that is the cosine ratio, and I'm just abbreviating. Sine is actually S-I-N-E, but we just use the first 3 letters, and that's adjacent over hypotenuse. And then we also have the tangent ratio, and that's the final 2 sides that we can pair up, which is the opposite and adjacent. And these are the 3 ways that we can pair up 2 sides of a triangle. And now we've got all 3. Okay, so for example, in this particular triangle, we have that, let's say the tangent of 31 degrees is equal to 3/5, right? And that makes sense because in the smaller one, the tangent of 31 degrees is 1.5 over 2.5, which is the exact same ratio, right? Based on similarity, okay? And so mathematicians recorded all of these different ratios for all of these different types of right triangles in a book. And now that information is all stored in the memory of your calculator. And we can use that when we're solving problems involving right triangles. So for example, you may have been asked last year to do something like this, where you know that this is maybe 42 degrees, and let's say this is 10.5, and you want to know this length, okay? And so you could now use a trig ratio to do so, because essentially what you want to do is like label your sides, right? So what are these sides called relative to the angle? Well, this is the hypotenuse. The x is the adjacent, and this is the opposite. So the side we want is the adjacent. The side that we have is the hypotenuse. And of course, we're using the 42 degrees because that's the angle that we have in the triangle. So we're going to use, we have hypotenuse, we want adjacent. We're going to use the cosine ratio because that uses adjacent hypotenuse. So I'm going to write out cosine theta equals adjacent over hypotenuse. And then I'm going to fill in what I know. I know the angle is 42 degrees. I don't know the adjacent, that's x. I do know the hypotenuse, that's 10.5. Okay, now to solve for x, I need to multiply both sides by 10.5 because I'm dividing by 10.5. So I'm going to go times 10.5 times 10.5, right? These will cancel. And then I'm going to go to my calculator. And I have to tell you, I'm using a calculator on an iPad. I really don't like this calculator because you have to enter things in a really funny way. But on this calculator, I think I have to enter the angle in first and then hit cosine. So I'm going to do that first. So 42 cosine and then times 10.5 equals, and that gives me 7.8. Okay, now one thing I need to mention is you can see in the left corner, top left corner, you can see DEG. That tells me that my calculator is in degree mode. When you guys set your TI calculators or your Casio calculators, when you reset the memory, it automatically puts it into something called radian mode, which you'll learn about next year. So you should know how to convert it back to degree. Make sure you do that. Okay, if you don't know how, then just ask and I'll remind you. Okay, so that's how you could use your trig ratios to find a side. Okay, we can also use trig ratios to find an angle. So for example, let's say I have another triangle that looks like this. And I want to find this angle here. And I know that this is 17 and this is 22. Okay. Well, again, I'm going to start out by labeling all of my sides. So this is the hypotenuse. Hypotenuse is always across from the right angle. So there's my hypotenuse. And then I want to label the sides relative to the angle that I want, which is the theta. So the side across from the theta is the 17, so that's my opposite. And then the other one is the adjacent, okay? Now in this case, I want the angle, and the two sides that I have are opposite and adjacent. So I need to use the tan ratio because that's the one that uses opposite and adjacent. So I'm gonna write out my ratio, tan theta equals opposite over adjacent, and then I can fill in what I know. This time I don't know the angle. So the opposite is 17 and the adjacent is 22. Now to get the angle, if you know the ratio, you have to use something called tan inverse, and you have to hit the shift button on your calculator and take the inverse of the ratio. Okay, so again, I don't like the iPad calculator because you do things in reverse. On your TI, this is exactly how you would enter it, or on your Casio, this is exactly how you would enter it. On these calculators, I think I have to hit 17 divided by 22 first, and then go second, tan inverse, and it gives me 37.7 degrees. Okay? So that is 37.7 degrees. Okay, so that's how you would find an angle using trig ratios. Okay, that's a very, very brief summary of what you did last year in Math 10C. And this is sort of considered pre-knowledge for what we're going to do in 20-1. The other thing I should just mention is that you remember your trig ratios. A lot of people use this mnemonic, which is so, ka, toa. So the idea is that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So if that helps you, you can use that as well. All right. Okay, so now I am going to move to your notes, and we are going to look at, today we're going to look at something called angled in standard position. And what essentially we're going to try and do in the first part of trigonometry in this course is look at how do we apply trigonometry to all types of angles in the Cartesian plane, right? So the Cartesian plane is essentially the x-axis and the y-axis. And the x-axis and the y-axis is divided into 4 quadrants. They're called quadrants. And I'm sure many of you guys have heard of these quadrants before. But the first quadrant is always where everything's positive. So that's over here. This is quadrant 1. And then you go counterclockwise. So this is quadrant 2. This is quadrant 3. And this is quadrant 4. And we usually use Roman numerals to label the quadrants, okay? Now, an angle is basically made up of 2 arms that connects at a vertex, okay? So one of those arms is called an initial arm, and the initial arm is always on the positive x-axis, okay? The vertex is always at the origin, by the way. So the vertex of the angle on the Cartesian plane will always be right here, okay? The initial arm will always be along here. Okay, so that's the initial arm. And usually we just assume that the initial arm is the x-axis. We don't even draw it in. So this is the initial arm. And then the terminal arm is essentially where the angle ends. Okay, so this is the terminal arm. And the angle goes counterclockwise. Okay, so this is one example. This would be an acute angle. Another example might look like this. Okay, so one arm would be here, and then perhaps the other arm might be here. Now you might think that this is an acute angle, but remember it always starts from the initial arm and goes counterclockwise. So this is actually the angle that we're looking at, and that's a reflex angle. It's bigger than 180 degrees. So always go in a counterclockwise direction. Okay, so this is an angle that is in standard position. Every angle in standard position has something called a reference angle. And a reference angle is the angle, the acute angle, that's between the terminal arm and the x-axis. So that's going to look different in every quadrant. So I'm going to draw each quadrant separately. Okay, so in Q1, and you can either call it RA, or I always grew up calling it this, theta R. So that's just my practice. I always call it this for reference angle. Okay. So in quadrant 1, okay, here is the initial arm. This is an angle in quadrant 1, so that's the terminal arm. This is our theta, and the reference angle is the angle between the terminal arm and the x-axis. Now that is actually just theta. So theta R equals theta. It's the same as the angle in quadrant 1. So if your angle is 67 degrees, your reference angle is also 67 degrees. Okay? In quadrant 2, here's the terminal arm. Or sorry, here's the initial arm. Here's the terminal arm. Okay, so here is our theta. And your reference angle is the acute angle that is between the terminal arm and the x-axis. In this case, that's actually this angle here. This is our theta R. Okay, now how do we get that? Well, theta plus theta R in quadrant 2 have to add up to 180 degrees because they make a straight angle, they make a straight line. So theta R in quadrant 2, whoops, I'm making a Q. Theta R will be 180 degrees minus theta. Okay, because the two of them have to add up to 180 degrees. Okay, in quadrant 3, let's see what this looks like in quadrant 3. Oh, I keep drawing thetas for Q's and Q's for thetas. Okay, maybe by the end of this I'll get this right today. Q3. Okay, so in Q3, our angle, here's our initial arm, and our terminal arm might be somewhere here. So this is our entire angle. That's our theta. But our reference angle is just the acute angle between the terminal arm and the x-axis. This is our reference angle, just that piece. Okay, now how do we figure that out? Well, it's basically the extra piece that's left over from the 180 degrees, right? So our theta R plus 180 is equal to theta. And so theta R is going to be the total angle, theta, minus 180 degrees. Right? So if you can imagine, let's say the terminal arm was at 190 degrees, then there'd be this extra 10 degrees left over beyond 180. So the theta r would be 190 minus 180. That's how you'd get the 10. Okay? And then finally in quadrant 4, Q4, there, I got it right that time. Here is our initial arm. Our terminal arm will be here somewhere. And our theta r is between the terminal arm and the x-axis, so that's right here. Okay, and of course this guy's here is theta. So how do we figure that out? Well, the entire circle is 360. So theta r is going to be the missing piece to get to 360, right? Theta plus theta r is 360, equals 360. So theta r in this case will be 360 minus theta. Okay, so this is what theta r looks like in all 4 quadrants. And this is how you would calculate what theta r is in each quadrant. Okay, and it's always, I should actually write this down, is always between the terminal arm and the x-axis. Okay? All right. So let's get into some questions. Determine the reference angle theta r for each angle. Sketch theta and theta r in standard position. Okay, so let's take a look. Our first angle is theta equals 75 degrees. Well, 75 degrees is between 0 and 90, so that actually happens to be in the first quadrant. So here's our terminal arm. This over here would be 90, where the y-axis is. So 75 degrees is about here, right? And our theta equals 75 degrees, and that's the same as theta r. That also equals 75 degrees. Okay? B, if theta equals 240 degrees. 240 is, if you think about, now sometimes it's helpful, and I should have maybe done this on the page before, to do this with the Cartesian plane. 0, 90, 180, 270, 360. So that when you get an angle, you can see what quadrant it lies in. So 240 is going to be between 180 and 370. That's in the third quadrant. So that is actually just, it's a bit closer to 270. Right, so here's our terminal arm and here's our theta. Now theta r is right here, right? And theta r is going to be the entire angle, 240, minus 180 degrees. And that is 60 degrees. Okay? All right, so let's try another one. Determine the angle in standard position when an angle of 60 degrees is reflected, A in the y-axis, B in the x-axis, C in the y, and then the x-axis. Okay, so let's take these one at a time. Okay, so we'll start with A. So first we start with 60 degrees. So that's like here somewhere. And then we reflect it in the y-axis. That's this guy over here, right? So we're going to have like a mirror image. And this is going to be our new angle, right? This will be our new terminal arm. And we want to know, what is the new angle going to be, right? Well, we have to kind of work out some symmetry and some geometry here. This over here is 60 degrees, which means this is also 60 degrees. That's like the reference angle, right? So if the reference angle is 60, the two of them together for the red angle have to add up to 180. So this over here has to be like something plus 60 equals 180. This theta is going to be 180 minus 60, which is 120 degrees. Okay, so that is A. For B, if we reflect in the x-axis, then we start with an angle that's at 60 degrees over here, and we're going to reflect this way. Okay, so again, this is 60, which means this is now 60, right? But the angle that we're measuring, the new angle, which is this one here, we have to start at the positive x-axis and go all the way around here, right? So now this red angle plus this 60 degrees has to add up to 360, which means the red angle is going to be 360 minus 60, which is 300 degrees. Okay, and then finally for C, we're going to reflect in the y-axis and then in the x-axis. So we start with the 60 degrees. And we're going to reflect here first. And then we're going to reflect here next. Okay, so this will be our final angle. And what we know is that this is 60, therefore this is 60, therefore this is 60. They're all going to have the same reference angles. Okay, now to get the red angle, we know that from basically here to here is 180, but then we have to add an extra 60 degrees. So the entire red angle is going to be 180 plus 60, which is 240 degrees. Okay? And one other thing we're going to talk about today, and this is a really important thing, which are special triangles. And there are 2.5 special triangles, because one of them is actually not a triangle, but it's also super, super useful. And special triangles are 3 triangles that come up all the time. There are 3 right triangles that come up all the time, where it's really, really useful to just know what the side lengths are for those 3 triangles, because we see those triangles or similar triangles to those ones, right? Triangles that are either bigger or smaller than those ones that are going to have equal proportions and therefore equal trig ratios to those ones all the time, okay? So the first one that I want to talk about is the 30, 60, 90 triangle. Oh, I want to do this in black though. Now, the 30, 60, 90 triangle comes from an equilateral triangle with a side length of 2. So an equilateral triangle is where all sides are the same and all angles are the same. So these are all 2 and 60, 60, 60. Okay? And what we're going to do is we are going to cut it in half. So I'm going to divide that in half, and that of course is going to make a right triangle. And when I do that, basically what I'm going to get is this. I'm going to blow it up a little bit so that we can see it a little better. But this will be 2. This along here will be 1 because it's this part, so it's half of 2. This will be 60. This will be 30 because that angle at the top was cut in half. And of course also because 60 plus 90 are the other 2 angles, that adds up to 150. So the third one has to be 30 because 150 plus 30 is 180. And we can figure out this third side using Pythagoras, right? So if we call it x for now, x squared plus 1 squared equals 2 squared. So x squared plus 1 equals 4, which means x squared equals 3, which means x equals root 3. So this is the square root of 3. And this is one of the triangles that you guys need to know. Because I may ask you, for example, what is the exact value of the sine of 60 degrees? And you would have to tell me the exact value of the sine of 60 degrees is root 3 over 2. Okay, that's the exact value. If you do it on a calculator, you're going to get a decimal approximation. You're not going to get the exact value. So that's one special triangle. And if you forget it, then don't worry, just draw out an equilateral triangle with a side length of 2 and cut it in half, and you can come up with it yourself. Okay, so that's one special triangle. The second special triangle is the equilateral right triangle, which is not the equilateral, what am I saying? The isosceles right triangle, which is the 45, 45, 90 triangle. And this one comes from taking a square with a side length of 1 and cutting it in half along the diagonal. So when I do that, what I'm going to get is this. And of course, I'm blowing this up just a little bit so that we can see it a little better. But I'll get 2 right triangles. I'm just going to draw one of them. These guys each have a side length of 1, and it's called an isosceles right triangle, of course, because it is an isosceles triangle as well. And these are each 45 because the 90-degree angles have been cut in half. And then we can figure out the hypotenuse using Pythagoras as well, right? So if I call that x for now, then I'll get 1 squared plus 1 squared equals x squared, which means 2 equals x squared, which means x equals the square root of 2. So that's the square root of 2. Okay, so this is the other right triangle that is a special triangle that is very, very handy. Okay, and I could again ask you, what is the exact value of the cosine of 45 degrees? And you would have to tell me the exact value of the cosine of 45 degrees is 1 over root 2. okay? You couldn't give me a decimal approximation there because I would ask for exact value, meaning you can't round. And then the third triangle, special triangle, that is not always taught, but I always teach it because it's super handy. And it's not always taught because, I'll tell you a secret, it's not actually a triangle. It's the 0, 90, 90 triangle. Okay, so it's not an actual triangle. Okay, and this one looks like this. Okay, this is 90 degrees. This is also 90 degrees. And this is 0 degrees. Okay, and then this is 1, and this is 0. So you almost want to think about two side lengths of 1 that are lying on top of each other. And there's actually no angle right here. Okay, so that's why it's not a triangle. Now the reason why it's helpful to have this though is that the trig ratios still hold up. So for example, if I want to know the sine of 0 degrees, well, I'd go opposite over hypotenuse. And the opposite is 0, and the hypotenuse is 1. 0 over 1. The sine of 0 is 0. Okay? If I wanted to know the cosine of 0 degrees, I would go adjacent over hypotenuse. 1 over 1. The cosine of 0 happens to be 1. If I want to know the tangent of 0 degrees, I would go 0 over 1. Opposite over adjacent. And it's also 0 degrees. Okay. If I want to know the sine of 90, I would go 1 over 1, opposite over hypotenuse, and the sine of 90 happens to be 1. If I want to know the cosine of 90, I would go 0 over 1, adjacent over hypotenuse, and the cosine of 90 is 0. And if I want to know the tangent of 90, this one's interesting, and you'll learn a lot more about this next year, that is 1 over 0. Which is undefined, and tangent of 90 degrees happens to be undefined, okay? So that's why I like to show people this triangle, because it gives you all of your trig ratios for those two angles, okay? All right, let's look at one more example, and then we'll be done for today. The pendulum arm of a metronome. So a metronome is something that keeps time in music, is 10 centimeters long. For one particular tempo, the setting results in the arm moving back and forth from the start position of 45 degrees to 135 degrees. What horizontal distance does the tip of the arm move in one beat? Give an exact answer. Okay, an exact answer means that we cannot round. Okay, no rounding. So we must have exact values. So you are probably going to have like a radical in there. Okay? So what we should do first is just draw this. When we're told that it moves back and forth from 45 to 135, those are referring to angles in standard position. So let's look at that. So one angle in standard position is at 45 degrees. And the other angle in standard position is all at 135 degrees. So that's about here. Okay, and the reference angle for the 135-degree angle is 180 minus 135. This is 45 degrees. And what that means is that this angle in here is right, because this is 45 degrees right here. This is 45 degrees right here. So those two together make 90, and the whole line makes 180. So the line between the two sort of extremes of where the arm moves on the metronome, that has to be 90, because 180 minus 90 is 90, meaning that this is a right triangle. Now we also know that the length of the arm is 10. Okay, and what we're being asked for is, what is this distance? Okay, now that is a right triangle, and it happens to also be an isosceles right triangle because these two sides are equal. If these are both 10, these two angles are equal, right? And those two angles have to add up to 90 because the angle that I've drawn in green is 90. 90 plus 90 equals 180. If they add up to 90 and they're equal, they are both 45 degrees. So what we're dealing with is this second special triangle. So what I'm going to do is I'm going to draw that out. And there's basically two ways that we can do this. You can use proportionality to find that distance. So based on this special triangle, we know that the ratios of the sides is 1, 1, root 2. And what we have is 10 and 10. Therefore, this has to be 10 root 2. So we've got our distance, right? Because we know the hypotenuse. Or you can just use Pythagoras, right? So if you know in your triangle that one side is 10 and the other side is 10 and it's right, it doesn't look right, but it is right. That's just a very bad drawing. Whoops, that's not X. This one's 10, and this is 10, and we're looking for X. Then we can just use Pythagoras. So 10 squared plus 10 squared equals X squared, and 10 squared is 100 plus 10 squared is also 100. 200 equals X squared. So the square root of 200 equals X, and then we have to simplify that, right? Because we want exact value. And 200 is 2 times 100. So that's going to be the square root of 2, or actually maybe I'll write it this way. The square root of 100 times the square root of 2. Which means X equals 10 root 2, because 100, the square root of 100 is equal to 10. And this is in centimeters. Oh, I wrote root X, sorry, root 2. Okay, so you could also just use Pythagoras as well. All right, so that would be your answer for that one. I'm going to leave it there for today.